Hello, everyone. So in this unit, we've been learning about heating curves and being able to identify what's going on in each section of a heating curve. And we've been learning about how the energy changes and what kind of energy is changing in the different sections. But today, we're going to focus on calculating. How do you calculate the amount of heat energy gained or lost at different points of a heating curve? It's one thing to understand what's going on. It's another thing to be able to use it. And so, yeah, we're going to learn how to do bit math today. Now, this first slide, you don't need to write. This is kind of like the old way of doing things. So when I was in high school, in addition to what we actually use now, we learned about calories. And you may or may not know that calories in your food is really just a measure of a calorie is the energy needed to raise the temperature of 1 gram of water 1 degree Celsius. So 1 gram is like 1 millimeter of water. It's like a big drop of water. So what they would actually do to figure out the calorie count in food is they would literally take a sample of the food and burn it in a cup. And the heat that would be released would leave out of the combustion chamber and heat the water up. And there would be a little stir to get the heat evenly distributed. And there was a thermometer. And literally they would burn the food and see how much the temperature increased. And they knew how much water they had. They knew how much food they had. So they could figure out the exact calorie count of the food, which is, I think, pretty cool. Now they've switched over to a different unit called the joule. This is the standard unit across all of science for energy. And this one's a little bit harder to picture. It's more of a derived unit, but the way you can think about it is the energy it takes to lift an apple off the ground 1 meter or 3 feet. That's 1 joule. And this table here has like the thing with joules is that they're a lot smaller than calories. Like, a can of soda might have 250 calories, and that's the equivalent of 1 million joules. Now, to be fair, the calories in that drink are technically kilocalories, and there's 1,000 calories per calorie that they list on the bottle. And so kind of in that same way, when we use joules in this class, a lot of times you'll see kilojoules or kJ as a unit, just so that we don't have to write giant numbers like this. So like if something was 10,000 joules, we would only say 10 kilojoules because it's 10,000s. So yeah, the unit of energy that we're going to be using is the joule. Oh, another way you can think of how much a joule is, your body every second is losing about 100 joules of energy as body heat to the air every second. And you're not losing like a ton of heat, so joules are pretty small. Okay, here's a thought question for you. Two objects are sitting out in the sun, a car full of air and a pool full of water. Which one's going to heat up faster? If you think about it for a minute, which one, if you're sitting in it, are you going to notice a temperature change first? Obviously, it's this car. The air heats up much faster than water. This is why after spring comes and summer comes and like the air might be like 80 degrees in June, you don't necessarily want to jump in the lake because the water is still back at like 50 something degrees. It's terrible. But also the converse of that, in the winter, the closer you live to the lake, the warmer it is. Like the lake stays warm for longer because it takes longer for the water to cool down as well. So the point is different materials heat up at different rates. They take different amounts of energy to heat up. So if we want to be able to do math about calculating how much energy does it take to heat up or cool down, if we want to calculate how much energy is gained or lost, then the first thing we need to know is what material are we talking about? What substance is it? Because there's this vocab word called heat capacity. Heat capacity is the energy needed to raise the temperature of 1 gram of a substance by 1 degrees. And different substances require different amounts of heat because they're made out of different particles. Those particles have different arrangements. Those particles have different masses and other properties. So they all heat up in different ways. Think about this pot of water sitting on the stove. You put the water in the pot, you turn on the stove, 5 minutes later, which of those are you feeling more safe to touch? The side of the pot or the top of the water? Personally, I would probably be okay touching the surface of the water, but I wouldn't touch the side of the pot. And that's because this pot has a very low heat capacity. It does not take very much energy to raise the temperature of a metal pot. The outside of the pot heats up super fast, whereas the water has a relatively high heat capacity. It takes a lot of energy to boil that water. You know, a pot that size, you might have to let it sit for 20 or 30 minutes before it gets to boiling, depending on how hot your stove is. So if we want to do math, one thing we need to know is what substance is it? And every substance has its own heat capacity. It's a specific number that you can find like in a table, or the question will tell you what that number is. Other things we need to know: how much energy does it take to boil that water? Well, we need to know how much water is it? What is the mass? It takes more energy to heat up more stuff, less energy to heat up less stuff. It's pretty straightforward. And how much are we heating it? Are we heating it up just a little, or are we like heating it all the way to boiling, or are we boiling it all the way away? And those are the 3 things we need to know if we want to do math with this. What is it made out of? How much of it are we trying to heat? And how much do we actually need to heat it up? So the formula that we're going to be using, the formulas we're going to be using are on your reference tables, on the very last page of the reference tables. So these are your reference tables. You should download them from the course website if you haven't already. Sorry, not course website, the course assignment list under course documents. Download the reference tables. And all the way at the end is a section called heat. And at first glance, this might look a little bit confusing. There's some weird letters, but they do define what all the letters mean over here. And probably the hardest part for you guys is there's 3 different formulas, and you're gonna have to figure out which of these 3 formulas to use for the problem. And I'll tell you clues and tips to help you look out for. So we're gonna look at this first one, that first equation. Q equals mc delta T. Q is the heat, M is the mass. So when they say heat, that's short for heat energy. There's the mass that we were talking about. We need to know the specific heat capacity that we need to know, and the change in temperature. How much are we heating it up? So let's go back to our example. So for example, how much energy does it take to heat 100 grams of water from 250 degrees Celsius to 50 degrees Celsius? So 100 grams of water would be about this much of the water bottle. It's not a ton of water. I will show you how I know that I need to use this formula. The big clue that I need to use this formula is the only one that has this triangle T. Triangle in science always means change. It's the Greek letter delta. So the change in temperature. And since the question talks about heating it from 25 degrees Celsius to 50 degrees Celsius, I know that there's a temperature change, and I'm going to use this formula. So as a reminder, the reference table tells us what each of these things mean. Since you don't see any symbols in between the letters over here, that means they multiply together. Like when in doubt, if there's no spaces or anything, or plus signs or minus signs, just multiply them. So really, this is a pretty straightforward formula. If you want to find the energy, you take the mass, multiply times the heat capacity, multiply times the temp, and that's it. Now for your classwork, I have it set up in such a way that you need to identify your variables first. And this is an extra step that some students grumble at, but I find it really helpful for organizing your work and making sure you plug the numbers in the right spot. So on the left-hand side, when I'm doing math like this, I take a moment to go through the question and write down all the things I know. So I'm reading here, how much energy does it take to heat 100 grams of water? I see that, and I'm like, 100 grams. G is for grams. I know that's the mass. So I would write down M equals 100 grams. I keep going, and I'm heating it from 25 degrees Celsius to 50 degrees Celsius. So I know that is the change in temperature. So I'm copying and pasting that because Triangle T is a pain to type. So how much is the temperature changing? If it's going from 25 degrees Celsius to 50 degrees Celsius, 50 minus 25, that's 25 degrees. And we'll talk tomorrow about having to change that to Kelvin sometimes. If you've got negative temperatures, be careful. We'll talk more about that tomorrow. So we got 100 grams, 25 degrees Celsius. They want to know how much energy. So the Q is the thing that we don't know. So Q is our question mark. And do we have enough to solve? No. So here in the middle, this heat capacity, if we want to solve it, this is our unknown. We need to know all three: mass, heat capacity, change in temperature, and we don't know it, at least from the question. But the question doesn't tell us because they know we have the reference tables. And what they do tell us is that this is water. And on the reference tables, we have a reference table for water. And it's on the very front page. So it's a little annoying for this topic, flipping from the heat equation you need to table B on the front page. But table B, physical constants for water. These are numbers just for water. And right here we have specific heat capacity of water. This is 4.18 joules per gram Kelvin. So 1 gram of water going up 1 Kelvin degree takes 4.18 joules. So I'm just going to take that number right from the reference table. And this is something you just kind of have to remember is there. It'd be easier if you had paper reference tables to look at and page through, but unfortunately, well, unless you have a printer. If you have a printer, I recommend printing out the reference tables. It would be very helpful. So our heat capacity taken off of table B is 4.18 joules per gram Kelvin. Luckily, Celsius degrees and Kelvin degrees are the same, so we can do that. Okay, so we went through the question. We took the information they gave us. We assigned them to variables. Now, last step, we just plug them into the right spots of the formula, and we solve. So what is our Q value? We don't know. So for me personally, when I solve these, I just leave the variable as the variable because I'm used to using different letters. If you like to always solve for X, if that's like a habit you've gotten into in math class, feel free to put like an X there instead of the letter. It's up to you. I'm going to keep it as I don't know what the energy is. So what was my mass? It was 100. When I'm doing the math, I don't bother to put the units in. Yeah. The heat capacity, C, is 4.18. And last but not least, the temperature change was 25 degrees. And that's it. Like that's all you got to do. That's a multiply symbol. That's stars multiply symbol. So when you do the math, I have not done the math, but I'm doing it on my phone right now. I get 10,445, 450. And my units, because this is heat, is joules. So that's me walking you through one example. The clue that you're going to use this formula is when there's a temperature change. Now, that's great for most of the time, but if we look at this heating curve, there's a couple of sections where the temperature doesn't change. What about when there's a phase change? It still takes energy to melt the substance. It still takes energy to boil the substance, but the temperature is not changing. So if we tried to use this formula up here with a temperature change, we plug a 0 in here and we'd end up with an answer of 0, which wouldn't make sense. We are heating it. It's just, it's not the kinetic energy changing, it's the potential. So we need different formulas for these two sections. So that's what those other two formulas are for. And if you have a paper copy of the reference tables, if you ever do, I strongly recommend writing a note to yourself that this is the formula for if you're melting or freezing. And the same for the other one is boiling or condensation. Yeah, sorry, messy. And you'll notice about these formulas, they don't have anything to do with a change in temperature, which is important because during melting and boiling, the temperature doesn't change. So this first one, think F for freezing, even though it says fusion. Fusion is like another word for freezing, kind of like it's the particles fusing together and locking into place. And the easier one might be to remember the one with the HV stands for heat of vaporization, which is a catch-all term for boiling and evaporation. Don't let these little sub letters here, these subscripts, confuse you. They just go with the letter that's next to them and they're meant to give you more information. So there's like heat for boiling or vaporizing, and there's heat of fusion, and they're just different kinds of heat. So let's use these formulas to do a little bit of math. Are we melting? So these are the clues you're looking for in the question. If you see a temperature change, use the formula from before. If you see melting or freezing, use this formula. If you see boiling or evaporating or condensation, use this formula. So a couple more examples. And how much energy does it take to melt 50 grams of ice? So the keyword there is melting. I don't know, I don't know what my Q is. I do know that the mass is 50, and we're assuming, because they don't necessarily say, whenever someone says melting ice, ice is what we call solid water. So for melting, we're going to use this formula. We know the mass. We're trying to solve for Q. The only thing we need to find is the heat of fusion. And once again, they don't tell us that in the question. So where are we going to get the heat of fusion from? The clue is that it's melting ice. So we're talking about water. So we're going to go back to our table on the front, table B, that has right here, the heat of fusion and the heat of vaporization. We already know exactly how much energy does it take to make 1 gram of water melt or 1 gram of water boil. So this shows us it takes much more energy to boil than it does to melt or freeze. So in this case, the heat of fusion is 334 joules per gram. So let me just make a note of that. My heat of fusion is 334 joules per gram. And now I just plug that into this formula here. And I'm gonna leave my unknown as Q. And Q equals the mass, which is 50 times the HF, which is 334. And that's it. So I get Q is equal to 16,700. Joules. Always remember to put units in your answers. Yeah. And so if you look at what I did, none of that was particularly complicated. The hard part is going to be remembering where to look. It's going to be getting used to these weird symbols and just like practicing doing it. Like the actual math, it's like basic multiplying. It's just knowing which numbers to put where. And yeah. I am running into a problem with screen sharing. We'll do one more example. How much energy does it take to boil 50 grams of, this should not say ice, this should say water. How much energy does it take to boil 50 grams of water? So because it's boiling, we know we're going to be using this formula. It's no temperature change when you're boiling. So we're going to be using this formula. And once again, this one's straightforward. We don't know the information we know from the question. Once again, the mass is 50 grams. We don't know how much heat, how much energy it's going to take. That's our unknown. That's what we're solving for. Tomorrow, and if you look at the classwork, there will be other things we don't know. The unknown will be in a different spot, but it's still basic algebra. And then this time, instead of needing the heat of fusion, we need the heat of vaporization. And once again, since we're talking about water, we just look at our reference table, table B, and now the heat of vaporization, HV, H sub V, that's 2,260. 2,260 joules for every gram of water. Then we plug our numbers in and we solve. So Q, we don't know. And to get the Q, we multiply the mass of 50 times the heat of vaporization, which is 2260. And this is 50 times 2260. 113,000 joules. Another way of saying that would be 113 kilojoules. And this is why we have kilojoules. So 113,000 joules. That K saves us from writing the 1,000, those 3 zeros. Okay, so that's a lot. And maybe not the most interesting. I mean, unless you are into calculating stuff. We will be practicing tomorrow doing this and more complicated versions of it. My request to you is that after you went through this and you took the notes, I'd like you to practice with the, move that down. Let's say number 1, number 2, and number 3. If you could do the first 3 today, we can go over it tomorrow, and then I can kind of help you out with more examples, troubleshoot, and yeah, just show you like how to do some of these other ones. Okay, sound good? I hope you do well. I hope you have a good day, and I'll see y'all tomorrow.